Moving on to part 2 of the fundamental theorem of calculus. Remember, part 1 said that the integral function is an antiderivative. So taking the integral of a function gives you the antiderivative of the function. And that's the starting place for part 2. Now, part 1 also went on to say when you take the derivative of the integral, you get the integrand back again. That's out of this. So let us evaluate the definite integral. So definite integral, evaluate the definite integral, we're going to get a number which represents the area under this curve. It represents the definite integral of this function. So step 1 is we're going to find any antiderivative of the function 2x cubed plus 1. So just as a little reminder to find the antiderivative, in this case we can use our backwards power rule. So when we take 2x cubed, remember we're going to add 1 to the power, we get x to the 4th. We're going to divide everything by that new power, so you'd have 2x to the 4th divided by 4, so you end up with 1/2 x to the 4th. The antiderivative of 1 is just x, and now any antiderivative, well, the most general antiderivative is where you add an arbitrary constant. But since the fundamental theorem of calculus specifies any derivative that we want, we're always going to let c be 0 because, after all, that's the simplest antiderivative. So any antiderivative would be f of x is equal to 1/2 x to the 4th plus x. That's just one of the many antiderivatives could be, and we're allowed to take any one that we want. So our function then is, we're going to take that antiderivative, 1/2 x to the 4th plus x, and we're going to evaluate it at 2 and at 0, and then subtract what we got. And there you go, equals 10. So here again is the list of the properties of the definite integral, and you should read through them pretty carefully, make sure that you understand what each one is telling you. Let's go on and let's do another example. And on the right, I've given you what the fundamental theorem of calculus part 2 says, and that is that the definite integral of little f of x is equal to the antiderivative of f evaluated at the upper boundary minus the antiderivative of f evaluated at the lower boundary. So find any antiderivative. Well, the most general one would be 2/3 x to the 3/2 minus 2x to the 1/2 plus c, and I hope that you go ahead and work that out so that you can go back and remember how to find antiderivatives. Your original function is x minus 1 divided by the square root of x. And remember, for antiderivatives, we don't have any quotient rule. So your best bet on that is to simplify first by converting square root of x in the denominator. That would be x to the 1/2. But then we want to simplify that fraction, so you would have x to the minus 1/2 times x minus 1, and then you do that algebra, and then go ahead and do the power rule. So it might take you a few minutes to kind of circle back in your brain how to do that, but give it a shot. Make sure you can do that. You should come out with this antiderivative. This is the most general antiderivative. And now a specific antiderivative, we just choose one, and we'll choose one where c is equal to 0. So we have 2/3 x to the 3/2 minus 2x to the 1/2. And fundamental theorem of calculus part 2 says, okay, now evaluate that at the upper boundary. So we're going to substitute a 3 in for the x. Evaluate it at the lower boundary. We're going to substitute the 1 for the x. And now subtract those two answers, and you should get 4/3. Here's another example. We have evaluate from 0 to pi over 6 secant of x times tan of x. Again, we want to find any antiderivative. Do you remember what the antiderivative of secant x tan of x is? In other words, what function has the derivative sec x tan x? Well, if you're remembering that it is secant of x, you are correct. The derivative of secant of x is secant of x tan x. So the most general antiderivative would be to add that arbitrary constant. We're just going to pick 0 for the constant to get a specific antiderivative. So f of x is equal to the secant of x. Now we have to evaluate that at pi over 6. So you're going to take the secant of pi over 6 minus the secant of 0. You're going to simplify that to get your answer. In this case, I have left it as the exact answer rather than putting it into the calculator to get an approximate answer. So you should have 2 square root of 3 over 3 minus 1. All right, one final example. What is wrong with this picture? Stare at it for a moment, take a pause, see if you can figure it out. Okay, so if you just proceed, you can take the definite integral from -2 to 1, which means you're going to find the antiderivative of x to the -4th. So an antiderivative where c is 0 is going to be negative x to the -3 over 3. Make sure you agree with that. And now we're going to evaluate that x to the -3 over 3, rather negative x to the -3 over 3 at 1 and at -2, so at the boundaries. And we're going to get an answer. What is wrong with this picture? Remember that the fundamental theorem of calculus requires that the function be continuous. So none of this works if your function is not continuous. So that's always something to think about before you get started. Is this function continuous? And it's not. All right, that's it.